Today's lesson is the first lesson in Unit 1. And before we get started, what you want to do is think back a little bit about the structure of an atom and pull out a periodic table because you're going to need both of those things for today. So thinking about the atom, you want to think, what are the three parts of the atom and where are they located? So remember, you have protons, electrons, and neutrons. And then you also have part of the atom called a nucleus. So the nucleus sits at the center of the atom, and that's where you find your protons and your neutrons. And then outside of the nucleus, around the nucleus, that part of the atom is a lot of empty space, but in that space is where you'll find the electrons. So keep those things in mind as we start talking about something called isotopes. So first we have to know, what are isotopes? So isotopes are atoms that have the same number of protons, but they'll have different number of neutrons. And we're talking about the same element here. So there's different isotopes of, for example, oxygen or chlorine. So these isotopes have the same number of protons, but sometimes some of them have different number of neutrons. And what this does is it's going to change the atomic mass of these isotopes. So if you have different number of neutrons, remember neutrons are in the nucleus, and the nucleus gives us the mass of the atom, we know the atom's going to have a different mass. When we look at our periodic table, if you don't have yours out yet, make sure it's handy. You should be able to find a mass on the periodic table. Now, if you're not sure where that is, there's a legend or a key on your periodic table, whichever one you're looking at, and find the mass. But what you might not have known about the mass is they're actually not a specific mass. It's an average atomic mass. And the average atomic mass comes from all of the naturally occurring isotopes found in the environment. And you can't tell how many there are or how much of each there are in the environment just by that mass necessarily, but it gives you an average. If we were to take all the different versions or isotopes of each element and look at their average mass, that's what it would be. If we want to represent some of those characteristics about isotopes, you'll often see them in a particular format that looks similar to this. And particularly what we're talking about here in red. So if you're looking at what you see in red, this notation here, it's called standard atomic notation. So if you see some information presented in this format with a chemical symbol for the element, just like what you see on the periodic table, and then you have some numbers that are superscripted and subscripted, so small numbers on top and on the bottom, that means you have standard atomic notation format. The number that's on the top is going to be your mass number, the mass of that particular isotope. And then the mass that's subscripted on the bottom is the atomic number. Now, that you should also be able to find on your periodic table. Most of the time, it's the number in the top right-hand corner. If you're looking at each element tile, there's a number in the top right-hand corner. Most periodic tables put the atomic number there. Now, coincidentally, the atomic number also matches the number of protons for that isotope. And often, just to represent things in more general terms, they give everything a letter designation. So the Z here is referring to atomic number, which also means protons. When we look at the mass number is the mass of the isotope. And how you calculate that, if you remember from grade 10, you take your number of neutrons, or neutron number, which you see down here, the symbol N, which you get here, and you add it to the number of protons. And then you have your mass if you had to add it up separately. Okay? Now, what if you just wanted to calculate the number of neutrons? If you didn't have it, if you're just looking at your periodic table, if you're looking at your standard atomic notation and your periodic table both, you would take the mass number of the isotope, which is the big number on the top, and you subtract it from the atomic number, which you find on the periodic table, and that would give you neutrons, if you didn't know what it is. Just to show you some examples of isotopes and how these particles can vary, let's take a look at 2 examples. There are many more than this, but let's take a look at 2. We'll look at hydrogen and then chlorine. So hydrogen has 3 naturally occurring isotopes. If you look, all of the protons are 1, but the number of neutrons vary. One isotope has no neutrons, one has 1 neutron, and the other one has 2. So if we look at the mass number, which we said is A, we take our neutrons, 2 plus 1 proton, gives us a mass of 3. Or this one, 1 plus 1 gives us 2, 0 plus 1 gives us 1. So you can see, depending on which isotope of hydrogen you have, you're going to have a different mass. Now, if we wanted to write one of these in standard atomic notation, let's say we take the one down here with mass number 3, you would take your symbol for hydrogen, and the symbol for hydrogen, if you remember, is just H, and we're going to put the mass number superscripted or on top. So I would put my 3 here. The bigger number is always on top. And my atomic number, or number of protons, 1 goes on the bottom here, subscripted. And that would be this particular isotope in standard atomic notation. Just for some contrast, here are a couple from chlorine. And chlorine has 3 different ones. They have mass of 35, 36, and 37. And you can see the protons are all 17. That's the atomic number of chlorine. But the neutrons again vary. So if you add neutron plus proton, you'll get your mass of that particular isotope. Now, one thing that hasn't been shown on this chart is how much of each are present. When you deal with isotopes, they're actually all not equal. So there might be 50% of one, and then 25% of the other, and 25%. Or it could even be more dramatic, 80% of an isotope, and then 10 and 10 of the other, or 15 and 5 of the other. They're all different percentages. So if we're looking at how much of an isotope is present in nature, or what we call the relative amount, we give it a special name called an isotopic abundance, and this is represented as a percentage. So if you're looking at, for example, nitrogen, there's more than 2 isotopes for nitrogen, but these are the most common ones. Nitrogen has 2 isotopes, and a shorthand form for this, nitrogen with an atomic mass of 14. If you look at all the nitrogen in nature, over 98% of it has a mass of 14. But if you compare it to nitrogen with a mass of 15, that isotope, you have maybe 0.368%. It's a lot less. So most of the isotopes or samples of nitrogen, if you were to look at them in nature, most of them are over 98% have that mass, but a small fraction have a different mass of 15. Now at this point, what I'd recommend doing is pausing the video, pausing the lesson video and going back to the lesson folder and watch the video that's posted on Introduction to Isotopes, because it'll recap everything we just watched, plus introduce the next part of the lesson. So watch posted clip on isotopes right now, and then you can come back and continue the lesson. I think that will help you understand the next part of our lesson. So hopefully you've watched that clip that was posted on what are isotopes, because now we're going to look at a special type of isotope. So what we're going to look at next are called radioisotopes. So in many cases, for atoms to be stable, they like to have the same or as close as possible number of protons and neutrons. Gives them some balance and stability in the nucleus. But what happens for some of them, sometimes adding an extra 1 or 2 neutrons in the nucleus makes them too unstable to exist in that format for a particular amount of time. What that does is it creates some energy, and these isotopes can't hold on to the energy. Think about you. If you've got lots of extra energy, it's going to be hard to sit still. You might want to move around, go get some exercise. So you need to get rid of that energy. Same thing's going to happen with the atoms. Atoms are going to start to decay, and decay means they're going to kind of break down, which means they're going to give away some of that energy. And in the process, you have changes in the nucleus happening. So they form other atoms, and in the process of that, they give off something called radiation. Now, you probably might get a little bit worried when you hear the word radiation. There's actually different types of radiation. You'll read a little bit about them, but nothing to worry about too much right now in our course. They're called alpha, beta, and gamma particles. Alpha and beta are a lot weaker. Gamma are the really bad ones where you hear stories about people getting radiation poisoning or exposure. So there's different strengths. Alpha ones are very weak. You can essentially block them with your clothing or a piece of paper. And then the gamma ones are the ones you need to worry about on a scale. So some will break down with some very weak radiation that's not harmful to us, and other ones will break down and give off more harmful information. Eventually, at some point, the atom gives off the right amount of energy, and then it's going to become stable again, and it'll have a new format, and that's okay. If you hear the word radioactivity, just for information, radioactivity is the actual release of energy or matter that comes from changes in the nucleus of the atom. Now, there's lots of other applications of these isotopes, and you may be able to research some of these along the way. But one place where you see radioisotopes being used is in radiation therapy in cancer patients. So one radioisotope that is used in radiation therapy is called cobalt-60. So it's an isotope of cobalt with a mass of 60, and it breaks down and releases off an electron, and this is actually showing beta decay. This is a beta particle, and it forms a new element here that's more stable. But that energy that's released goes into the radiation part of radiation therapy. Now, how this all actually happens isn't something that we cover in our course. If you do take grade 11 physics, the types of nuclear reactions involving different types of radiation, those are ones that are covered there. So we don't cover that here in our course. You might read a little bit in your book about it, but if you're interested in learning more, let me know and I can get you some resources. Okay, now that we've done some background on isotopes, what we're going to do is learn how to calculate some numbers. So how is that average mass on the periodic table actually calculated? Or how do we actually calculate the percentages or isotopic abundances of isotopes? So you need your periodic table handy for this, and you'll definitely want your calculator handy. So if you don't have those, again, grab them right now because we're going to walk through a couple of different problems together. Okay, so first what we're going to do, we're going to have some data and we're going to learn how to calculate the average atomic mass. Remember, this is the mass on the periodic table that you see for different elements. So if you look up the mass on the periodic table, this is how you would calculate it. So we're going to do an example with magnesium. Magnesium has 3 different isotopes. So the first isotope, magnesium 24, has a mass of 23.98 U, which is atomic mass units, and a percentage of 79. So that means out of these 3 isotopes, 79% of all magnesium in the environment has this mass. Just for reference, let's put down what U means here. So U stands for atomic mass units. Okay. The next isotope, which we shorten magnesium 25, has a more specific mass, 24.98 U, and 10% of magnesium has this mass. And then magnesium 26 has a mass of 25.98 U, and 11% of it in the environment has that mass. So now what we're going to do is calculate a weighted average. We're going to use a few different symbols for this. So we'll write down a formula. We're going to see U with our units, but there's going to be an M. This is going to be for mass. And then we're going to see percentage, which means abundance. So here we have 3 isotopes, so we're going to need 3 parts to our formula. So the formula starts off with average mass. And what you do is you take your first mass, and it doesn't matter which one we call 1. We could just go in order. So this could be number 1, magnesium 24, M1. And we're going to multiply it by its percentage. We'll just call it %1 for now. And we want it in its decimal form, which means we're going to need to divide it by 100. You can put it in fraction format, or you can just go right to the percentage. It doesn't matter. But we have 2 other isotopes, so I need to put 2 more expressions in here. So my next one, number 2, is going to be magnesium 25. So mass number 2 times percent number 2, and you guessed it, it's over 100 again. And mass 3 times %3 over 100. Now when I go and put the numbers in my formula here, even though it gives me the shortened mass beforehand, if they give you a more specific value, one that's more accurate, more information, you go with that one. So my first isotope has a mass of 23.98. Always put our units in. And we're going to multiply it by the percentage, which is 79 over 100. Or you can just go right ahead and put in 0.79. It doesn't matter. Next, mass 2 is going to be for magnesium 25. But again, I want to use that more accurate number. So 24.98 U times 10 over 100. And then I'm going to go with mass number 3, which is going to be my last isotope here. So 25.98 U times 11 over 100. Now, once you've done all this, the rest is just math. You need to plug this in your calculator and solve. Again, if it's easier for you, just change these right away to decimals, and then it's easier to plug in your calculator. So this would be 0.79, this would be 0.10, and this would be 0.11. When you do all of that, you should get approximately 24.30, and we're going to put our units in there, U. So the average atomic mass for magnesium is 24.30. Here, when we put our answers, use 2 decimal places. If you've heard of something called significant digits, when we do more calculations later on in the course, then we'll come back to that. But for this type of problem, 2 is just fine. So that's one type of problem you'll run into where you'll have to calculate average atomic mass. Let's try another problem. What if instead of calculating the average mass, they ask you to calculate the isotopic abundance, the percentage? So let's look at this question and break down how we're going to tackle it. Boron has 2 isotopes, boron 10 and boron 11, and we have specific masses for each. We want to calculate the relative abundance of each isotope. Again, remember, if you hear abundance, it means find the percentage of each isotope. So before we even start, let's just organize what we have and what we're trying to solve for. So we have boron 10. Boron 10, its mass, which we'll call M1, is 10.0129 U, and we want to find out what its percentage is. So we're going to call it %1. Then we're going to do the same thing for boron 11. It has a mass, we'll call it mass 2 because it's the second isotope we have, 11.0093, and %2, we also don't know what that is. Okay. We're also going to need the average mass of boron. Now that was not given to us in the question. So sometimes they'll give you the average mass in the question, and in like this case they don't. If they don't, you actually already have that answer on your periodic table. So what do? You go to your periodic table, look up the mass of boron, and it's 10.81. Depending on which periodic table, it might vary, but the one that we use in class has it as 10.81. And just as a reference, this is from your periodic table. Okay, so we're going to need that later. But now if you remember in math, when we're solving, we need to have a variable when solving unknowns. Here we've got 2 unknowns. So some people might automatically think, okay, 2 unknowns, I need 2 variables, x and y, but we don't have enough information to solve for 2 different variables, x and y. So we're going to use a little trick here. Percent, when we think about percentage, remember it has to add up to 100%. Okay, we always think percent and it has to equal to 100. So no matter what this number is and this number is, %1 and %2, whatever they end up being, we know has to equal to 100. So this is helpful for us because now what we could do is rearrange this and we could come up with an expression for our percentages. So what if we wanted to create something for %1? We would keep our 100 on the right hand side, but move %2 to the other side. And since this is positive on the left, it's going to become negative on the right. So now we have an expression here, %1 is equal to 100 minus %2. So we can change this up here and say now, well, %1 is going to be equal to 100 minus %2. And you may want to highlight this or put it in a different color on your paper just so that you can come back and say, well, where did I get this again? And now that you have it kind of noted, or maybe a star beside, you can say, okay, that's how we came up with that particular expression. So now we're only solving for %2 because we have this unknown and this unknown. If you don't like using that %2 as a symbol, you can also put an X in instead. It's all the same in the end. Now we go back and we're going to organize all of our information into that formula we used before in the first question. So remember this one, average mass, and it's going to be equal to M1 times %1 over 100 plus M2 times %2 over 100. I only have two parts to my formula because there's only two isotopes here. If I had more, I would add on more, but we only have two. So now I can go and start putting in my numbers. What's my average mass? Well, remember we made a note of it up here. Average mass is 10.81. That's from the periodic table. So I can put that right in. And then I can start to fill in my information. M1 we had from our question, 10.0129 U, and it's going to be multiplied by our expression for %1, which we said was 100 minus %2, and we have to put that over 100. And we're going to add that to our second mass, which was 11.0093. And again, multiply it by %2, but we don't need to use that. We go back up. %2 is just our unknown, so we're going to just put that in as is. So now you can see our unknown here is %2 and %2. They're both the same. Don't forget that's over 100. And now all the rest of this question is math. Now you can take as many steps or as little steps as you need to, but I know a lot of people don't like to work with fractions. So at this point, the best thing would be to get rid of fractions. So if you remember the trick from math, anything that's on the bottom of a fraction, you're going to multiply the top by the same. So remember, since everything here is being multiplied, this is all one big bracket. I can multiply this by 100, which will cancel out my 100s. I can do the same thing here. This is going to get multiplied by 100. So this is going to cancel with that. But over here on my left-hand side, don't forget that. I have to multiply this side also by 100. But since there's no fraction on the left, I can't eliminate it. So if we simplify this, after we've made those adjustments there, we're going to have 100 times 10.81. We'll do this in steps just to make sure everyone's on board. Then we're going to have our mass times our percentage here. We have to use brackets here because we're multiplying, minus %2. And this is going to be added to 11.0093, and then it's %2. And now we can start multiplying. 100 times 10.81 is 1081. Here we have to do our order of operations. Remember, what's outside the bracket you have to multiply in. So first we're going to multiply by 100. So we get 1001.29. And then we have to do the same thing again and multiply it here. So minus 10.0129 %2. And here this is already done for us. So plus 11.0093 %2. Okay. Then if you remember from math, when you're solving, you have to put all like terms together. So these first two numbers have no unknowns, no x. Remember, this is like our x. So we're going to move this number to the left-hand side and subtract it. And we're going to group or add these two numbers together. So minus 10 plus the 11 with all the decimals in there and combine them. So we move this over and add it and make sure that you add these two together. And you'll get 79.71. And on the other side, 0.9964. And then if you remember, when you want to find your unknown, we have to divide. So 79.71 divided by 0.9964 from numerator to denominator. And that's going to give us our %2. So when we do that, our %2 is 79.9979, which we can round to make it a lot easier. So we'll say it's about 80% is %2. So this is for our second isotope. But don't forget, we need to find %1. So now if we want to find %1, we're going to take 100 minus 80, and that's going to give us 20%. So when we're calculating here, we have our two abundances. Isotope number 2 has an abundance of 80%, and isotope number 1 has an abundance of 20%. So most boron, 80% of it will have a mass of just over 11, and the other 20% will have a mass just over 10. So lots of practice with both theory and calculation problems will be part of your homework. There's a few other variations and twists on the calculation problems, but these are the typical two type you'll find. Finding the average mass is often a little bit easier. The percentage, a little bit harder, but only because there's a few more steps with math.